Everyone is obsessively arguing over whether TSMC or Intel will win the nanometer race, but they've forgotten a brutal truth. No matter how small the chips get, AI is starting to devour the global power grid. We aren't just hitting the edge of physics anymore, we are hitting the absolute limits of thermodynamics. The real winner in the next 5 years won't be found in Silicon Valley. It's hiding in copper mines and electrical substations. Think about it. We've spent decades cheering for smaller transistors, faster processing, and sleeker software. We treated the cloud like it was made of air. But in 2026, the illusion is shattering. That cloud is actually made of massive steel buildings that generate enough heat to boil rivers and consume enough electricity to power entire nations. While retail investors are chasing the next NVIDIA killer or debating 2-nanometer yields, a massive bottleneck is forming right under our noses. It's a bottleneck of wires, transformers, and raw energy. In this video, we're shifting the lens. We're moving away from the microscopic world of chips to the macroscopic world of infrastructure. I'm going to show you why the golden age of AI software might be headed for a thermal wall, and more importantly, which overlooked sectors are set to become the ultimate gatekeepers of the AI revolution. If you want to find the real alpha in this market, you have to follow the electrons. Let's dive in. To understand why energy is the Achilles heel of AI, let's look at what is actually happening inside a single $40,000 chip. We've been conditioned to believe that smaller is better. We see TSMC announcing 2-nanometer nodes, or Intel pushing into the angstrom era, and we think, great, more efficiency. But here's the paradox that the industry rarely talks about. As transistors shrink, power density explodes. When you pack billions of transistors into a space the size of a fingernail, you aren't just creating a processor, you're creating a heat element that rivals the surface of a star in terms of energy concentration. This is the hidden wall of the AI revolution. For decades, we relied on something called Dennard scaling, the rule that as transistors got smaller, their power density stayed constant. But that rule is dead. It's broken. Now, every time we shrink a chip to make it faster, it leaks more electricity and generates more heat. TSMC's megachips and Intel's PowerVia aren't just cool engineering flexes, they're desperate attempts to keep these systems from melting themselves alive. Let's put some real numbers on this, because the scale is staggering. Every time you ask ChatGPT a simple question, it consumes roughly 10 times more electricity than a standard Google search. One query, 10 times the power. Now multiply that by billions of users, 24 hours a day. We're moving from a world of light digital browsing to a world of heavy generative compute. According to recent projections, by 2030, global data center electricity demand is expected to double, or in some aggressive scenarios, triple. We are talking about adding the equivalent of the entire power consumption of a country like Germany just to keep AI models running. For giants like NVIDIA, Microsoft, and Google, the most important metric is no longer just teraflops or raw speed. It's shifted to something much more grounded: cost per token. If it costs 5 cents in electricity to generate 1,000 words of text, but the competitor finds a way to do it for 3 cents, the game is over. In a narrow-margin world, energy efficiency is the only moat that matters. This is why Microsoft is literally scouting locations near nuclear power plants, and Google is investing in small modular reactors. They aren't doing it to be green. They're doing it because they are terrified of running out of juice. Think about the physical reality. You can't just plug a massive H100 GPU cluster into a standard wall outlet. These data centers require high-voltage transmission lines and dedicated substations. But here's the twist for the investors watching this. The world's electrical grid is aging. It wasn't built for this. In many parts of the US and Europe, the waiting list to connect a new data center to the grid is now 5 to 7 years. 5 years. In the tech world, that is an eternity. You can have the most advanced 18A Intel chip in the world, and you can have the most brilliant LLM ever coded, but if you don't have a transformer and a power line to feed it, that hardware is just an expensive paperweight.
We are witnessing a fundamental shift in the power dynamics of the tech industry. The software as a service era was easy because the marginal cost was near zero. But the AI as a service era is a different beast. It has a physical price tag, paid in kilowatts. This brings us to a massive blind spot in most portfolios. If everyone is crowded into the chip makers, but the chips are hitting a thermal and energy wall, then where does the value go? It flows downstream. It flows into the boring stuff that most Silicon Valley analysts haven't looked at in 30 years. We are talking about the physical backbone that makes the cloud possible. But wait, if everyone is rushing to buy high-flying chip stocks, who actually cashes in when those chips require gigawatts of power just to stay awake? That is where the real alpha is hiding. And it starts with a material that humans have been using for 10,000 years, which has suddenly become the most high-tech asset on the planet. I'm talking about the red gold of the AI era. But wait, if everyone is rushing to buy high-flying chip stocks, who actually cashes in when those chips require gigawatts of power just to stay awake? Welcome to the world of the boring stuff, the unglamorous, heavy-duty industrial sectors that are quietly becoming the ultimate gatekeepers of the AI era. First, let's talk about the red gold. I'm talking about copper. You see, you can't move massive amounts of electricity from a power plant to a data center without it. AI data centers require roughly 3 to 4 times more copper than traditional ones because of the sheer density of power they consume. Think of it this way. If the AI chip is the brain, copper is the entire nervous system. But here is the problem for the market. We aren't mining enough of it. It takes about 15 years to bring a new copper mine from discovery to production. Meanwhile, the demand from AI, combined with the global shift to electric vehicles, is creating a supply-demand gap that is terrifying. When you have an asset that is essential, non-substitutable, and physically scarce, that is a recipe for a massive structural re-rating. As an investor, you have to ask, do I want to bet on the crowded software race or the physical metal that every software company is forced to buy? Next, we have to address the heat problem. In part 1, we mentioned how chips are becoming miniature suns. Traditional air cooling, basically just giant fans, is no longer enough. We're reaching the physical limit of how much heat air can carry away. Enter liquid cooling. This isn't just a niche upgrade, it's a total infrastructure pivot. We're seeing a transition from air-cooled data centers to liquid-to-chip or immersion cooling systems. This is a massive high-growth tailwind for companies that provide specialized pumps, coolants, and thermal management systems. In the AI gold rush, these companies are the ones selling the ventilation systems for the mines. Without them, the $40,000 NVIDIA H100 in your server rack becomes a molten lump of silicone in seconds. Finally, we hit the biggest bottleneck of them all, the transformers and the grid. Most people think that if you have money, you can build a data center anywhere. Wrong. The bottleneck isn't capital, it's the queue, specifically the interconnection queue. In many jurisdictions, the lead time for a high-powered electrical transformer has jumped from months to years. Why? Because for 30 years, we neglected the grid. It was boring. It worked well enough. But now, AI demand is slamming into an aging 20th century infrastructure. This has created a fortress value for companies that already own power-connected land and for the industrial giants that manufacture the transformers and switchgear. If you follow the logic of a strategic researcher, you'll realize that the bottleneck is where the profit is. In 2023, the bottleneck was GPU supply. In 2024, it became HBM memory. But in 2026 and beyond, the bottleneck is the ability to physically plug the machine into the earth. It's a classic picks and shovels play, but with a twist. This isn't just about supporting AI, it's about the fact that AI cannot exist without a massive, physical, and extremely expensive upgrade to our physical world. So we have the chips, the brains, and the infrastructure, the body, but there's one more layer to this. If energy is the raw material, how do we actually value these companies? How do we distinguish between a utility company that's just stable and one that is an AI growth engine? That brings us to the ultimate comparison. We need to look at how the titans, TSMC and Intel, are positioning themselves in this energy-constrained world, and more importantly, how you can build a portfolio that thrives even if the grid is under pressure. Now let's get tactical. We've identified the energy wall and we've seen the boring stuff that holds the keys, but as an investor, how do you actually play this? Who is better positioned for a power-hungry future? The execution king, TSMC, or the aggressive innovator, Intel? When we look through the lens of energy, the comparison flips. TSMC is the master of efficiency at scale. Their strategy of building bigger cities through advanced packaging is actually a massive energy play.
By stitching chips together closely, they minimize the distance data has to travel, which drastically cuts down on power leakage. For the big tech buyers like Apple or Nvidia, TSMC is the safe haven because they deliver the highest yield with the lowest energy overhead per chip. If you believe the future belongs to whoever can scale AI without collapsing the grid, TSMC is your bull case. Intel, on the other hand, is swinging for the fences with structural transformation. Their power via technology, moving power delivery to the backside of the wafer, is a direct answer to the thermal bottleneck. It's riskier, it's harder to manufacture, but if Intel pulls it off, they might achieve a performance per watt breakthrough that makes current chips look like steam engines. Intel is the wild card. It's a bet on radical innovation solving the energy crisis before the competition even realizes how high the wall is. But the opportunity doesn't stop at the chip makers. To build a truly resilient AI energy portfolio, you have to look at three specific pillars. First, the utilities. These are no longer grandma's dividend stocks. In the AI era, utility companies with nuclear or hydro assets are the new oil barons. Look for providers that have direct behind-the-meter contracts with data centers. When a tech giant signs a 20-year deal to buy every megawatt a plant produces, that utility isn't just a service provider, it's a high-growth infrastructure partner with guaranteed cash flow. Second, power infrastructure. We are talking about the guts of the grid, the companies making the high-voltage switchgear, the liquid cooling manifolds, and the specialized transformers. These are the enablers. Even if Nvidia is replaced by another chip designer, even if the AI software landscape changes completely, the physical need for power management remains. This sector offers a structural moat because the barriers to entry, patents, manufacturing scale, and regulatory certifications are incredibly high. Third, strategic mining. This is the raw material play. Beyond just copper, look at the supply chains for materials like silicon carbide or high-purity aluminum used in massive heat sinks. However, we have to talk about the bear case, geopolitical fragility. The energy wall has a political shadow. Most of the raw materials we need for this infrastructure are concentrated in a handful of regions. A single trade war or a regional conflict doesn't just raise prices, it stops the AI revolution in its tracks. If the world fragments into geo-economic blocks, the cost of these materials won't just go up, the supply might disappear. Investors need to monitor resource nationalism as closely as they monitor interest rates. If a country decides to keep its copper or its power for itself, the global AI supply chain hits a dead end. So how do we sum all this up? The AI revolution is a physical event. It's a massive redistribution of capital from the digital world back into the physical world. If you're only looking at the screen, you're missing half the story. You have to look at the ground. You have to look at the wires. You have to look at the heat. We've traveled from the microscopic gates of a transistor to the massive scale of the global energy grid. We've seen why the math is terrifying for some, but a goldmine for others. But after all this analysis, there's one final question that determines everything. In a world where compute is limited by power and power is limited by physics, what does the end game actually look like? Is it a permanent energy crisis or a new era of abundance? If there is one thing you take away from this analysis, let it be this: AI is not just a digital miracle, it is a physical reality. It is matter, it is heat, and above all, it is energy. Investing in AI while ignoring the power infrastructure behind it is like buying a Ferrari and forgetting that the world is running out of gasoline. You can have the most brilliant algorithm in existence, but without the copper, the cooling, and the gigawatts of electricity to feed it, that code stays silent. The energy wall is real. It is the new boundary where the digital revolution meets the laws of thermodynamics. As the hype cycle around software begins to settle, the market is going to realize that the true gatekeepers of the future aren't just the ones writing the prompts, they're the ones controlling the flow of electrons. So I have to ask you, looking at your own portfolio right now, how much of it is dedicated to the raw hardware in infrastructure standing behind the AI curtain? Are you still betting 100% on the apps and the software, or have you started following the energy trail? Let me know your thoughts on the utility and energy sector in the comments below. Is the energy wall the biggest threat to AI or its greatest investment opportunity? And if you want to see how this physical reality is being reshaped at an even larger scale, don't miss my deep dive into the Terafab project, where Elon Musk is trying to solve this exact power-to-chip equation. Thanks for watching. Stay sharp, watch the grid, and I'll see you in the next one.